Thank you, Dave. Can you all hear me?
Yes.
Excellent. Good. Thanks, John, for inviting me and for being persistent in tracking me down and pinning me to a date. So for most of my professional life, I've been an angry young man. I think that's starting to improve, and I've been angry because of the lack of launch systems in this country. Despite the fact we have a very successful space industry, we haven't done launch, which is getting into space, and that made me very cross for a while. I think things are starting to change, so I'm getting a little bit less angry, and it's hard to be angry this evening because it's lovely. So I'm going to talk about technology. What technology do I need to get into space? Why is it difficult to get into space? What is an orbit? What is a suborbit? A little bit of history, because those who cannot remember the mistakes of the past are sadly condemned to forever repeat them. And some practicalities. What is it like to deliver a satellite into orbit today? Why is it difficult? And why could it be made a lot better? And how could we, as engineers, past, present and future, make a difference in the UK? So I'll start with a picture. A long time ago, not 50 years ago, so I'm not quite that old, my parents took me here to, and some of you may recognise this, this is the Isle of Wight, and that's the Needles there. Now at the time, there was none of this exotica there. There was some lumps of concrete all looking a little bit sad, and I sort of said, well, what's this all about? And they said, oh, that's the former testing site for the Black Arrow rocket. And I thought, that sounds exciting. Where can I find out more? And the best they could show me was a slightly rusting plaque saying, former rocket test site. So I asked around as I grew up and went to university, and I said, where are the rockets? And the best, although the most depressing answer I got was out of the then space agency. We had a BNSC, a British National Space Centre, or British Nominal Space Centre, as the Americans like to call it, because it was 7 people in an office not far from Victoria. And I said, where are the rockets? And they said, we don't do rockets. And I went, well, why not? Well, we don't. Go and do something else. And I was obviously not happy with this. That started making me angry, and I got angrier over the years, particularly when I realised that we'd done this on the left in 1971, which was the year I was born. And it was staggeringly successful, amazingly cost effective, and utterly ahead of its time. And what's left now is this. I popped down to the Science Museum in South Kensington the other day. I've often been there, it's a bit of a pilgrimage for me. And I took a picture of what hangs from the ceiling, and that's the last Black Arrow. That's a real rocket, that's not a mock-up. And that is a superb, brilliant piece of engineering that quite nicely eclipses the piece of American Saturn Moon Program engineering which sits on the plinth behind it. And I keep thinking every time I go there, why aren't we doing this? And it's very important that we realise why we should be doing this. And for that, I need to talk about something called value. Government loves to talk about value or value chains. Industry and engineering and all the mandarins in Innovate UK and places like that love the idea of a value chain. So value chain is this. It allows you to take usually a technical product, do something with it to provide something that somebody wants. So here's an example of a small satellite. This is Martin Sweeting, Professor Sir Martin Sweeting, who I used to work for, and he invented the small satellite. Small means a few hundred kilograms, size of a washing machine or a microwave, perhaps even smaller as compared to bigger ones that can be anything from a car up to a bus size. And these things are pretty clever, much cleverer than I am. And they do all kinds of neat stuff, and they cost a lot of money. But they're no use whatsoever sitting on the ground, despite all the technical stuff surrounding them. What do? Well, there's a whole range of satellite applications, and I'm not going to go into those this evening, but they take pictures, that's one thing. And they take pictures of things that cause problems. So down on the bottom left, there is an example of a forest fire. This one was taken in California in 2006. It's in what's called false colour, so California doesn't look that red, fortunately for them. But you can see where the fire is, where the wind is blowing it, to a certain extent where it's been, and you can make some predictions as to where it might go, and then once it's finally sorted itself out or been put out, you can make some estimates of the damage that's been done. And all that's done from space. You never have to go there, although California's a jolly nice place, and you can do it all remotely. And that's one of the fantastic uses of satellites, and there are many others I won't talk about them this evening. In order to get from here to here, you need this. Pointy thing on one end, hot bit at the other end, loosely speaking. I'll go into a bit more detail later. But you need a rocket, because this satellite is no use at all sitting on the ground in what's called the clean room. And that, very simply, is the space value chain. And somehow, in the last 40 years in the UK, we kind of missed that very important point, because we do this, we turn information from satellites into incredibly valuable data products. I'm sure most of you have got a smartphone. Smartphones, to tell you where you are, not only use the mobile phone masts, but when you're out of range of those, they use GPS, which is an American-built satellite system, and they use a whole host of other things. One of my favourite apps is the Met Office weather app, not because I'm really into apps, but because I like to know whether it's going to rain on me when I step out the door. And that one takes a huge amount of data from satellites, and the Met Office is really good at that. So we do apps, information, data products. We do satellites, big, small, in between, lots of other things, but we don't do this bit. And that has been a major failing of the British space industry. And it's taken, somewhat ironically, the government probably until 2017, because we started building satellites in the 1960s, taken them until 2017 to realise that we were kind of missing a key bit of the puzzle. So, to get the satellite into space, what is actually needed? Now, there's a couple of technical terms that I'll use, one of which is called suborbital, because space is not actually very far away. If I were to go straight up, it's about 60 miles. So it's roughly the distance that I drove from home in London, South London, to Oxford today. 60 miles, straight up. And whilst there's a bit of technical involvement required to do that, it's not that difficult. There's a bit of energy involved, and you need some wings and something to boost you up, but it's not that hard. Getting to space is not the problem. Staying in space is much more difficult. And the earliest astronauts actually went straight up and came down again in what was called a suborbital trajectory. So they launch from the surface of the Earth, they shoot up, go as fast as they possibly can, and come back down again. And there are many examples of powered flight with wings. I'm not really a wing person, although I imagine many of you in the audience are quite fond of wings. There are many examples of winged vehicles, very high performance ones, that flew up to the edge of space and beyond, and then came back down again. They didn't have enough energy to reach space. In order to do that, you have to try a little bit harder. And very roughly speaking, it's 30 to 40 times as hard to go into what's called an orbit and stay in space compared to just going up, touching the edge of space and coming back down again. So at this point I need to go into a little bit of, not arithmetic, but a little bit of sort of technical stuff. But I thought I'd start with this. So this is a neat plaque that I discovered hiding on the internet today, and it's from, I'm trying to remember the name of the place where Isaac Newton was born. It's up in Lincolnshire. It's a very nice hall, actually. I'd quite like to visit it. And under one of the apple trees, about 350 years ago, Mr. Newton, possibly before he became famous, was sitting, and an apple fell, perhaps several apples, we don't really know, nobody was there to actually record it, but so the saying goes, onto the ground. And he started thinking about this thing called gravity. Gravity's a funny thing, because you might not realise this, but if you look at the person next to you in the room, you're actually gravitationally attracting them. And they're gravitationally attracting you back. Not by very much, because fortunately people don't weigh very much, but if you start talking about planets, which are slightly larger, they have a lot more mass, a lot more stuff. So their force of gravitational attraction is much higher. And for that reason, if I want to go up into space, well, I could try jumping, but I'd have to be pretty good. I think, Usain Bolt and then some, but I'd come back down again, because gravity is the law. In my house, it's also my wife, she's a lawyer, but outside of the house as well, gravity is also the law. And it means that in order to get into space, you need two things. You need altitude, and you need velocity. You've got to go up, you've got to go fast. How much though? Well, I mentioned 60 miles. That's just to the edge of space. That's really just kind of scraping the surface of it. In order to stay in space, you need to be about 250 kilometers up, so about 4 times. And that, again, is not that hard. It's not a huge distance in cosmic terms. But this is the really tricky one, 8 kilometers a second. How fast is 8 kilometers a second? Because I live in London, and the average traffic speed 8 kilometers an hour if you're lucky. So I thought about this for a bit, and I thought, okay, how long's the UK? Well, it's about 1,400 kilometres from John O'Groats to Land's End. And if I were to get in my car, and if I believe what Google Maps or Apple Maps told me, it would take me maybe 14 hours to drive solidly with no breaks from end to end. It's traffic dependent, obviously. I wouldn't start in London. 14 hours. If I were to get on my bicycle, because I'm a keen cyclist, and pedal as fast as I could without stopping, it would take me about 14 days, more or less. That's typically what most cyclists take. Again, some of the Tour de France ones will probably do it in less. 14 days. If I managed to get up to orbital velocity, 8 kilometers a second, it would take me slightly under 3 minutes to go from one end of the UK to the other. And that's why people like Tim Peake have such an amazing time. They go right round the Earth in 90 minutes, and they get 16 sunrises and sunsets every single day. The lucky bugger. I'd really like to have his job. I did apply for his job, but clearly the better guy got it. So it's difficult.
Sorry to interrupt. Could you try and put the microphone
Higher up. Apparently Is that any better? Hello? Still all hearing me? Good. Apologies for that. So it's difficult to get into orbit. You've got to go high. You've got to go really, really fast. What is this orbit thing? Well, I brought a few props because I've spent most of the last 8 years teaching at university. Here's a globe, my favourite globe. It's really good because you can draw on it. And I'm super pleased that my wife bought this for me. It's one of the best birthday presents I've ever had. So I'll mark on the UK, which is sort of somewhere around here. Here are our friends in Europe, somewhere over there. And then if you go over to the other side, here's America, Canada, South America, etc. And the Earth rotates in this particular direction, so while the sun rises in the east and sets in the west. An orbit is really a path. It's like a racetrack, an invisible racetrack in space. And you can have orbits of different sizes. I borrowed my kids' hula hoops for tonight. They didn't really mind, but I'll have to take them some biscuits or something for tomorrow. And an orbit, if you imagine it, it sits in space. You can't see it, but it's an invisible pathway that satellites, Tim Peaks, space stations, all manner of other things follow. And the orbit, as you can see from here, can be in different places. It can be sort of like that. It could be like that. It could be at some inclination. You could have a small orbit, or you could have a big orbit. And you can set it up by virtue of applying some energy to your spacecraft or your satellite, kind of however you want within reason. There are some very high orbits indeed, where things actually rotate, go around the Earth at exactly the same speed the Earth rotates. So as the Earth slowly rotates, the satellite, where's my satellite? Well, we'll take a space shuttle, that'll do, appears to hang in the sky over the Earth in exactly the same spot. So there's kind of orbits 101. Why is this important? Because we want to get into an orbit in order to be positioned in space to do useful things, such as looking for fires, communicating, sending navigation signals to our phones, all these things. The challenge is doing that. The launch phase, the part of the space mission which involves getting the satellite from the ground up to where it can do its job, is brief. This is good. It is extremely intense. There is an enormous amount of vibration, of shock, of thermal loading. It's the worst possible day you could imagine in an aircraft when everything goes wrong, and then some, because you're dealing with so much more energy. Best aircraft we have fly at perhaps 2 or 3 times the speed of sound. In orbit, to get into orbit, you're trying to get 25 times the speed of sound. And managing that energy is a huge challenge. Some of you may have heard, though, that we're interested in launching satellites into space from the UK. Why would you launch from here? I mean, green and pleasant land, particularly this evening. Well, I'll explain using this picture, which is pretty unusual for a number of reasons. First of which is there's almost no clouds. Very unusual day in the UK, a bit in Scotland, but that's normal. Second thing is, these pinpoints here are potential spaceport sites that have put themselves forward and said, we want to be a spaceport, we think it's a great thing, could do with the business, we like rockets, nothing else going on here of interest, etc. And you might notice that they're all in reasonably sort of out of the way places. Well, it depends whether you class Newquay as out of the way, Wales not too far away, but northern Scotland definitely, up in the Shetland Isles, somewhere up there, yes, out of the way places. Reason being is that space launch involves lots of energy. It's difficult. Sometimes things go wrong. And when things do go wrong, you don't want the general public anywhere near it. They'd love to be there, taking pictures and posting it on Twitter, but trust me, a launch vehicle failure is rather like a small nuclear explosion happening. And if you do some sums on the energy, that's actually fairly close to the truth. You might think, why on earth do we want launch at all? Well, I've told you why, because it has huge value for our space industry. So we have to pick the spot that's most remote and has one other particular characteristic. You might remember I said, well, the Earth rotates from east to west. If you follow the rotation of the Earth, you get a bit of an extra bootstrap. You get a boost from the fact the Earth's already moving. In fact, it's worth about 12.5% of that 8 kilometers a second you want to deliver, which is really worth having, particularly down at the equator. It's a little bit less near the poles because the Earth is physically moving a bit slower there. Okay, but you want to go in that easterly direction. Who do we have to the east? Angela Merkel, French gentleman, I forget his name, but he thinks very highly of himself. All our good friends in Europe. And as you know, our relationship with Europe, as mentioned earlier by the President-elect, is not at the best at the moment. So if we were to start launching, even from our most remote places, and go in the best direction, we would make ourselves even unpopular and possibly hasten Brexit. That's a topic for another night. So what can we do? Because we want to launch our satellites. Oops. We can, as it turns out, launch in a northerly direction. And this is a very special form of orbit that's called a polar orbit. Because if you imagine the spacecraft going around in its orbital track like this orbit is situated so the spacecraft travels over the poles. And the Earth slowly rotates, and the spacecraft goes round and round and round. And over a period of time, not too long, you actually get to see, if you're in the spacecraft, if you're a camera, the entire surface of the Earth. And that's incredibly valuable from a remote sensing and a monitoring of the Earth, and let's face it, a spying perspective as well, if you want to know what the bad guys are doing. In order to do that, you have to fly north. And very conveniently, with a few small exceptions, there is not a huge amount of stuff in the way that could cause problems if your launch vehicle failed. So we have an opportunity in the UK, and in fact nowhere else in Europe really has that. There has been some launch work going on in Norway and some in Sweden, but for the most part France, Germany, Spain, all our good friends to the east of us don't have that opportunity. In fact, Europe launches its rockets from the other side of the world. They take them to French Guiana in South America, which is a very long boat ride and quite inconvenient because it's the middle of a very hot, sweaty equatorial forest, whereas north of Scotland is quite pleasant for a lot of reasons. So what must our rockets do if we're going to do this launch? Obviously, place the payload, the satellite, the doing thing in the desired orbit. But preferably do it without breaking it. Satellites are full of electronics. Electronics, barring perhaps mobile phones that we throw on the floor on a regular basis, are quite sensitive. So the satellite needs to get there and still function. It would help. The rocket has to perform reliably. No point if it blows up on the launch pad, then you have to build another satellite, the insurers get involved, it all gets very messy. The rocket must operate responsively. That's to say, go as soon as possible when you say, I've got a satellite, it's built, it needs to go now. And if you're a military customer, that is even more important. Flexibly, go to a range of different orbits. This one, that one, some other one. It really depends what you're looking at, which orbit is best, so you need to be able to access a range of different orbits. And of course, last, very important these days, it's got to do it economically. No point keeping on pouring money into rockets that actually just cost the government money. We've got to try and do these things as commercially as possible. This is a colossal challenge, and it's a challenge I think that my generation, hopefully guided by some of the experience from the previous generation and with the young upstarts who aren't here yet, we're going to rise to that. We want to do it because it's challenging. As Kennedy said, we choose to go to the moon not because it is easy, because it is hard. It's a difficult challenge, and I'll show you why. But to understand that, we need a bit of history. So here are some early rockets. This one, I'm sure you'll recognise. I went to Peenemünde a few years ago. It's a very interesting place. Lots of discussions on billboards about swords into ploughshares and philosophy and all that sort of thing. This one is the Redstone, which launched America's first astronauts into suborbital space, so up and then straight down again. I think it was Alan Shepard who said, "Boy, what a ride!" But he was only there for 7 minutes in space. This was what came next, the Atlas. And over in Russia, which was much less publicity sort of focused at the time, the R7, the Little 7, was also launching. And of course, they got there first with Yuri Gagarin. What can we notice about all of these? Well, they're all pointy. No wings, really. Fins, perhaps, but that's about it. They're all single stage, so they're one rocket unit in each one of those, possibly with a couple of extra motors on the bottom. They all used liquid propellants. Rockets have been around for a very, very long time indeed, but they're just fireworks. And not really well suited to the purpose of putting things into space. These use liquid propellants. They had to be mixed and controlled in very careful proportions. They all used what's called inertial or internal guidance, so measuring their position by means of sensors on board to steer them very precisely up and down and along and into that orbit picked by the designers. This was still 60-something years ago. Fast forward another 10 years or so. Things in some ways aren't looking that different. They're still long and skinny, there's a pointy bit at one end, there's a hot bit at the other end, but there are some subtle differences. Each rocket is composed of multiple ones, what are called stages, and when each one finishes its fuel, it drops away. What else can we say about these? They use different rocket propellants. So in the early days, it was just liquid oxygen and kerosene, jet fuel. Now they're starting to use hydrogen, higher energy, much more difficult to handle. Hydrazine, highly toxic, but doesn't boil and evaporate away like liquid oxygen and liquid hydrogen. A number of other features. The Proton, in fact, was originally, this is the Russian Proton, developed to throw a nuclear warhead 10,000 kilometers the other side of the world. Can't imagine why they wanted to do that. It's a good thing they decided it wasn't really worth doing. They were left at the end saying, well, what do we do with this? Oh, we can put satellites into space. The Saturn, which, as you well know, I'm sure, put the Apollo astronauts around the moon, onto the moon, and this was the Titan, which was used to launch all manner of things, including the Gemini astronauts and many satellites after that. While the rest of the world was busy, we were also getting in on the act. So we built something called Black Knight, which was a sounding rocket. This was a suborbital rocket whose only job was to go up, take some measurements, and come down again. It was also used for military purposes. It was designed to test re-entry technologies for warheads. So some of them went up, turned around, fired another engine, and came back down even faster and dug a very big hole in the desert, but sent some very useful data back beforehand. And that was unbelievably successful and very, very cheap. 20-something launches, no failures, unheard of in the rocket world. We messed around with missiles for a while until we realised that having a cryogenic propellant, liquid oxygen, that you needed to tank into the launcher right before launch, before you lit the blue touch paper, wasn't going to help if you only had 7 minutes warning that the Russians had decided to launch missiles against us. So we spent lots of money on the engines, the rockets, the launch silos, and then decided actually it was probably obsolete before it was built. But it then went into a future European programme, which we subsequently left because we decided we weren't into European launches. The success story here, in addition to this one, is that, and I've mentioned Black Arrow before, October 28th, 1971, 28 days after I was born, it delivered our one and only satellite into orbit. We have built many satellites since, and we continue to do so, but we've always relied on other nations' launches. And after that outstanding success, we became the one and only nation on this entire planet to have built a space launch capability and given it up. 6, 7, maybe 8 nations at the most have the ability to launch things into space. We're the only one that did it and said, no, we're not interested. That is why I was an angry young man for a while. And the real irony is that this is a small satellite. Prospero weighed about 100 pounds, 50-something kilograms. Nowadays, we make small satellites in the tens and hundreds per year, and I work for a company, Surrey Satellite Technology, that does that regularly. We could so much have done with that Black Arrow to make our lives easier, but it wasn't there. Moving onwards, though, with the history lesson. So America realised that throwing away the rockets after they delivered their satellites into space was not the best idea, and said, you know what guys, we need a reusable space truck, kind of a Chevy Blazer that can get these things into orbit, no problem. It can take everything from pigs and corn and you name it up there, and it can just come on right back down, wash it down, hose it down, fill it up full of fuel, and we're good to go again, guys. So of course everyone in America thought, hey, that's really great, we've got to have a piece of that. So all the different agencies piled in, the National Reconnaissance Office, the Department of Defense, the Department of Commerce, NASA, you name it. And of course, they ended up with a rocket designed by committee. It was very high tech. The maintenance, repair and overhaul, or MRO, for those of you in the aerospace industry, was horrific because it was so full of bits of technology that people wanted to try. The engines were the best engines ever built, and then some, but they had to be completely stripped down and rebuilt each time. And in the end, this thing was so expensive they couldn't fly it as much as they wanted, and they had to spend more time maintaining it. So this was, despite being a very impressive piece of engineering, it was a dismal economic failure. And the Americans would probably disagree with that because it was a flagship for them. It delivered parts to the International Space Station. They used it to deliver and repair the Hubble Space Telescope. It did many amazing things, but it did not demonstrate the benefits of not throwing away rockets. Fast forward another few years. This chap, if you can see him, probably not from the back, made his money in the internet world. He's a South African originally. He was responsible for Zip2Go, then PayPal. He now does hot rod cars running on electric motors, interestingly. And he's called Elon Musk. He's quite a nice guy, actually. I've actually met him once or twice, and he's very kind of down to earth. That's a bit ironic, isn't it, really? Anyway, that's his Falcon 9. That is a pretty big rocket, but it's nothing compared to what he's got planned. That's one of the first launches of this thing. And at this point, I might try and cue a video. This is probably where it will all go wrong, but we'll give it a try, just to sort of show you his recent Falcon 9 launch. We'll see if this will work. Let's have a go.
The fairing is Elon's cherry red Tesla Roadster,
Right.
and inside of it, a passenger. His name is Starman, but don't worry, he's not human. But he is donning the SpaceX-designed spacesuit that our human astronauts
So this is the
will be wearing.
payload for the rocket, mostly because rockets blow up the first time, so you don't want to put anything too valuable on them. This is his Falcon Heavy launch, some of his team. Not many women there, that's a bit disappointing. So this is particularly neat because he aimed to get most of this rocket back, and nobody else in the world does that right now. So some of it's animation, some of it's real footage, and it's actually quite hard to tell the difference at times. You can see some data from the rocket on the far side, how fast it's going, how high it is. So those are the boosters that have dropped off, and normally they just fall in the ocean or burn up or squash or otherwise just be disposed of. But he's going to get them back. He's realised that recycling rockets is pretty important. He turns them around, fires up the engines again, brings them down. And the most amazing thing is they both come down at exactly the same time, and that's real footage. Not only brought the rocket back, brought two bits of it back within 100 yards of each other at the same time. So that bit goes on into space, and then what's called the core module is going to come back. And he brings that down onto a barge in the ocean. Now I'll just stop there because that was the bit he didn't quite get right. It kind of landed a bit hard on the barge and went sort of boom, but I think he'll get it right next time. And there's more footage there, and you can find that video online. It's quite good actually. I'll just skip ahead one slide and just show you a bit of what's called the trajectory. And I don't want to get too technical here, but he starts from here at Cape Canaveral or Kennedy Space Center, flies due east because that's the way rockets want to go. You've got lots of Atlantic Ocean then before you get to Europe, so good for Elon Musk. The boosters go to a certain point and then turn around and come back. Brilliant, done that. The core stage he's going a bit further and a bit faster, so it's harder to bring that back down to the launch site. So he drops it onto this thing he calls the drone barge in the middle of the Atlantic Ocean, then slowly floats it back. And the top bit eventually goes on into space. He doesn't recover that, still pretty expensive, so he's like to get that back in the future, and he's working out how to do that. And ultimately that would be a fully reusable rocket. What made me really sad, though, about Elon's business is that he used to own a part of the company I work for called Surrey Satellite Technology, and before he got into all this showmanship and this aerial ballet and all that great stuff, he had a small rocket. Perfect for our small satellites in the UK. Pretty cheap. 10 million bucks, job's a good one. How many do you want? Did launch from somewhere in the middle of the Pacific, so it was a trifle difficult to get to the launch site. But Falcon 1 was brilliant, and we thought we want those. And then he went off and said, you know what, I'm done with Falcon 1. Small beer. Never going to make any money out of that. He was largely right. I need the bigger stuff. So this was his training rocket for his bigger one. Very sad for us, which again made me angry, because I thought there was our rocket for the UK. Didn't mind that it was technology built over there, but I thought we could bring that here and we could do some great stuff with it. But he went, nah, going to cancel that. Moved on to the bigger stuff. And this is where we are today in Europe. We have this thing called Ariane 5. It's a lovely piece of engineering. It really is. Again, like SpaceX, like the space shuttle and everything else. And it's about the same weight on the ground as one of these. Fully loaded Airbus A380, Ariane 5. Costs not too different. I think a 380 is about 250 million euros. Ariane 5 is about 150 million. The big difference, this works for about 15 minutes and it's thrown away. Brilliant if you're a French rocket motor builder or a German payload fairing builder or any of the other people, because we don't have a big role in this because it keeps you in a job for life, keeping on building these things all the time. Whereas this thing flies backwards and forwards across the Atlantic, round the world, unbelievably reliable and used again and again and again. So in the future we've got some lessons to learn about how to make rockets work a bit more like aircraft. What goes into a rocket then? Lots of different bits. This is a simplification really. You've got different stages. Each one is really a self-contained rocket in its own right. The first stage gets the thing up, gets it going, gets it moving fast, tries to get it above some of the atmosphere that really gets in the way. Then you have to break that away and you have an interstage or a separation system. It allows for clean separation. Then you fire up the next engine, go a bit higher, a bit faster, break that one away when the rocket fuel's gone. Another interstage, and you might or you might not have a third stage. It depends on the design of the rocket, and there's arguments both ways. And then eventually you get to the top, you have a fairing, a cover to protect the satellite from weather, which is disposed of fairly quickly, and Elon Musk is trying to get those back. And people said to him, well, why do you want to get your fairing back? And he said, well, would you want to throw away $5 million every time you launched a rocket? And people went, oh yeah, that makes good sense. And then finally, under the fairing, the satellite payload. So those are the main bits of a rocket. The bit that is the most challenging, the others are not without their challenges, but the most challenging one is the propulsion. So I'll see if I can get another video to run. Where's my mouse gone? There we go, let's try this.
All rocket types need two basic ingredients, fuel and oxidizer, so that the fuel can burn. Solid fuel rockets are the most common. Here a powdered mixture of solid fuel and oxidizer is packed into a casing. Once it's ignited, the mixture rapidly combusts, propelling the rocket forward. It's very simple and safe until it's lit, but has one drawback: it's not easy to turn off. In a liquid rocket, liquid oxidizer and fuel are kept in separate tanks. These are then pumped into a combustion chamber where they react violently with each other, sending hot gases out of the specially shaped nozzle. The rate at which the liquids are pumped can be varied to alter the amount of thrust, and it can even be shut off altogether. But if these liquids accidentally made contact outside of the combustion chamber, they could cause an explosion. The third type of rocket uses elements of both other systems. The oxidizer is stored separately, and the fuel forms a solid lining on the inside of the rocket tube. In Bloodhound, the oxidizer is high-test peroxide, or HTP. It is pumped through a silver-plated catalyst, which causes it to decompose, releasing very hot steam and oxygen. This is hot enough to ignite the fuel itself and create thrust. It's a fairly safe system, as stopping the flow of oxidizer will stop the rocket, and the fuel is a harmless rubber mixture.
And on that note, I brought some rocket fuel with me today. So I'll let you pass it around. It is absolutely harmless unless you throw it at someone very hard, I suppose. Big thank you to Bloodhound, who I used to work with, for putting that neat little video together. Interestingly, the hybrid not widely used in space launch systems, is a big part of Virgin Galactic and Virgin Orbit's business, as they've decided hybrids are possibly the safest and simplest way of making sure their astronauts, their high net worth individuals, make it up to space and come back again. More on Virgin Galactic in a minute. So the propulsion bit is the critical bit. I am biased. I've spent the last 10 years or more of my life working on rocket engines, but it's pretty difficult. There's an example of a gamma chamber, of which they had 8 in the back end of Black Arrow. It's not very large, as you can see, and you think 8 of those sent that 20-ton rocket off the launch pad and delivered that small satellite that's worth so much money into space. I thought that was pretty impressive, and then I realised that we didn't make those anymore. I thought, what would it take to make one of those again? And there are some bits that are difficult. It's largely a materials challenge, because this bit gets very hot indeed, 2,500 to 3,000 degrees centigrade, extremely hot, so you have to cool it. You've got to pick the right materials. But the really difficult bit is sort of down here, and this is the pump system. To drive those propellants in there and push them out with enough force to get that rocket off the pad and get it really going to those 8 kilometers a second, you need pumps. A lot of pumps, and some really challenging pumps. We're not talking, pumps that go in your fish pond in the garden or pumps that drive your shower. This is the kind of pump that can empty a reasonable sized swimming pool in under a minute. So it's ultra high performance, and that's a cutaway of it. You can see all these spinny bits and all these thick sections of metal and many other colour-coded parts. There's a massive wiring and fluid lines. There's these things called turbines that are really the power source to drive the pump. And I work with a little company called Lena Space that's working on building a turbine for a rocket pump for the first time in 50 years in the UK. The other bit over here is the shower head. It's the injector. That's the real black art bit of the rocket engine. The pumps is some pretty scary but well understood engineering. The rocket engine is, I would say, largely material science. This is the tricky bit. You've got to get those 2 propellants, something like jet fuel and hydrogen peroxide, or jet fuel and liquid oxygen, to come out, mix in just the right proportions, atomize, vaporize, burn smooth as silk, as opposed to with an enormous great bang, because really a rocket is a very carefully controlled explosion, and do it with that. And that injector design is very difficult indeed, and we still don't have the computer tools to actually model that properly. SpaceX, don't they have lovely rocket engines? And they put all these pictures online. I think it's fantastic. So they start out beautifully chrome buffed and shiny, and you can see these are a bit bigger than the Gamma ones. Okay, obviously the Falcon 9 is a bit larger, and there's lots of them at the back end. They do their test firings. It's actually, as rocket engines go, it's not a super high performance one. It dumps the output from the turbine overboard, and this is this black cloud of rubbish coming over there, which is partially burnt turbine gas. It's like, when you fire off the afterburner on a lot of jet aircraft, you actually get a black plume of stuff which is unburnt or not completely burnt fuel. What's really interesting about SpaceX, though, is that over the years of launching their Falcon 9s and starting to get them back, they've built over 600 of these engines. 600 of these things, and these are pretty expensive. They're probably a few $1,000,000 a piece. And Elon quite rightly said, you know what, we built them as cheap as we possibly can. We've learned a huge amount through building 600 engines about how to build them as efficiently and as reliably as possible. But guys, we've got to start getting them back. We have to do that. And that is a key part of future rocket science and launch vehicles, is getting the difficult bit back and refurbishing it and flying it again. There's another bit that's tricky as well. So the propellant tank. The problem here is that launchers, because of the energy they have to put into the satellite to get it into orbit, are largely rocket fuel, propellant, typically 90 to 95%. That's a fairly large number. A typical car is probably 5 to 10% car fuel. Okay, so there's a big difference between those two worlds. There's some examples of ones we built. So this is Blue Streak up at the National Space Centre, and this is one of the sections from it on a trolley, a dolly up at Spade Adam that I took years ago, which is up in Cumbria. So we figured out how to do that, but we have lost that know-how, and we have to build it back again. And the solutions are largely twofold. Smart material science. So instead of metal, composites is a big interest, because you can make them lighter, stronger, stiffer, and generally better for a lot of applications than metal. It's not quite that simple, but composites have a lot of attraction for rocket tanks. The other thing is to be really smart from a structural engineering point of view. One of the smartest ideas I've ever come across is this. Oh, actually, there's a composite tank we built. Kingston University was a small company. So the blue colour, if you can see that, is actually the liquid oxygen. So this is carbon fibre composite. We chopped the top off because we had to do some internal analysis. It's bubbling away, but quite happy with liquid oxygen, which is not bad when you think that epoxy in the carbon is a pretty good fuel, and you just poured liquid concentrated oxygen in there. But the fact is, it's so cold, it doesn't react. It just slowly evaporates. And we were quite happy with that, and we're going to see if we can build bigger ones. But the smart structural engineering is kind of this. So a good example is the sort of soda pop bottle, or actually, if I've got one here, the Coke can. Now, what have these got in common with rockets? Well, the fact is these are both about 95% the good stuff, or water if you prefer it, I don't know. So that one is actually 98% water, 2% the stuff that holds it. This one's about 95% Coke and about 5% can. And that's what you've got to achieve for a rocket. But a rocket is hundreds of times larger. It contains truly unpleasant stuff. Either it's freezing cold, it's incredibly oxidizing, it's unbelievably toxic, or sometimes it's all three. How do we get this to the scale that we need for this? It's actually very simple. And I can show you this because if I were to squash this and try and crush it as hard as I can, it's pretty rigid. Some of that is the Coca-Cola because liquids aren't very compressible. But if you open it up, there's probably a cue for a quick drink actually. I didn't put the rum in earlier, unfortunately. If I put some of that in there and wait for the bubbles to settle, this thing suddenly becomes really flexible and squashable and collapsible. I won't crush it anymore, otherwise I get a fountain of Coke coming out. And it's known as, in this rocket, because we applied this principle 50-something years ago and then forgot, it's called the steel balloon. So it's very, very thin stainless steel, about as thin as a Coke can. And inside you've got rocket fuel and you pressurize it with a gas, nitrogen. And because of the pressure of gas, it goes incredibly rigid. And in fact, it was pioneered over in the States by a Belgian called Charlie Bossart, who was a brilliant engineer. You know, I aspire to be half as brilliant as him. And he came up with this idea for a steel balloon and figured out how to make it, which is very difficult, and invited a bunch of visitors to come and see his prototype. And they kind of went, what, that's your rocket? Paper thin, you could sort of see the rumples in it. And he said, okay, I'll pressurize it. It's pretty tough now. And they went, nah. And he went, okay, here's a big mallet. Go on, take a clock at it. And they did, and the mallet just bounced off, and the thing was absolutely unscratched. If you also reinforce it with some ribs down the side, you make it even stiffer still, and it becomes unbelievably light to the point where it can be 95% rocket propellant and 5% structure. And that's what we need for the structural and the tank side to get into orbit. And that's something we have to remember how to do in the UK over the next few years. The bit that I won't say too much about tonight, because rocket engines, structures and avionics, they're the three difficult parts of launch vehicles, is this bit. This is a block diagram, and it shows, well, you might think either that's trivial if you've got an electronics background, or that's really complicated. It depends on your point of view. Rocket avionics is all about steering the rocket, working out where it is, where it needs to go, sending the right signals, and then steering the rocket engine usually. And what we're doing now is we're taking some really neat stuff, like single board computers, Raspberry Pis, and saying, can we, with all that massive amounts of computing power that we now have in a tiny, tiny package, actually do all those functions? It's not quite that straightforward, because Raspberry Pis don't work in real time. They're kind of slower than you think, even though they process very fast. Okay, so they can't react very fast to things. They're not especially reliable. They tend to break. All of the things you need to be a good rocket engineer. But the technology is there, and with a bit of adaptation and a bit of good old British smartness, I think we could crack that third problem as well. You need a few other bits. You've got to have places to store your propellant and load them. You need to track your rocket, probably from multiple places. You can actually get the rocket to do a lot of its own tracking using GPS these days, so this may become less important in the future. You need to load and attach your satellites into the rocket, And of course, if you're building rocket engines, you have to test fire them, and that's what I've spent a lot of my time over the last 10 years doing. And the objective of this is simple: low cost, small satellite launch for the UK. That's what we need. Meanwhile, over in Europe, we have some rockets. They're quite nice. They're all launched from the ground. Ariane 5 I mentioned earlier. This is Soyuz, that Europe borrows from the Russians and launches from French Guiana. This is Vega, which is built mostly in Italy. And we launch those. They're all launched from Kourou in French Guiana, so it's a long, long trip to get there. It's a pretty expensive journey. The logistics costs of servicing that spaceport the other side of the world, good though it is, are very high. The annoying thing is that the supply chain for those rockets and getting the satellites in there, and this is an example satellite with that payload shroud going over it. These are the people you can see working on it, so it's pretty big scale stuff. The supply chain for that is closed off to us. UK decided a long time ago it didn't want to contribute to European launch programs, and as a result we get very little business from that, which is unfortunate because we have the know-how, we have a lot of the technology. But that scale of rocket, that giant thing, perhaps launched from the ground, might not be what we need for our satellites. So there might be some other approaches. In the late 1950s and early 1960s, the X-15 was probably the most successful high-performance flight demonstrator ever built, just under 200 flights. Fastest one went to Mach 6.72. The astronauts came out of this program, routinely flew to 50 or 60 miles or more, and it came back again. Fantastic achievement, all dropped from an aircraft in the first place, so kind of like a mobile launch platform. Fast forward 60 years, Richard Branson thinks he can do better, so that's actually Launcher 1, which will deliver a small satellite into orbit. And this obviously is Spaceship 2 and the White Knight 2 carrier, which I did a bit of work on several years ago. We hope we can attract them over to the UK because we're telling them that Newquay's a pretty nice place. It's got a pretty long runway. It could operate there. You could come and have a nice holiday, and you can fly out over the fairly not too busy Atlantic Ocean and launch your satellites or do your space plane, in fact. So this is a space plane designed to take tourists up to the edge of space, bring them back again, ride of a lifetime, rock star treatment, all those good things that Virgin tells us. This one is the workhorse delivering the small satellites into orbit. Small satellites, that's not one of them. Okay, there. We do build those, most of them, not entirely. It's more of a European thing now. We build some of them. That's what we build. That's what we're really, really good at in this country. Not just down in Guildford, but also, somewhat incongruously, up in Glasgow. That's Clyde Space, actually set up by an engineer who used to work for him, decided he'd go and do his own thing up in Scotland, and more companies are popping up, building some pretty small spacecraft. CubeSats, they're called. This is what the need is for. And the way they get into space right now is they catch the bus. Big satellites can afford a taxi. I've always been a bus person personally, okay? But small satellites have got to catch a bus, and the bus kind of works like this. There's your bus, your rocket, you attach a bunch of different satellites, you build a kind of a Christmas tree sort of shaped thing behind it, and you plug the satellites in one by one, and you make sure no one drops anything. You click, and off you go. And sometimes the bus gets pretty crowded, as you can see, and when the rocket fails, as they tend to do, a lot of bus customers get very upset, but there are still a few companies, including quite a successful UK one, brokering that bus service. We don't build the bus, but that's how small satellites get into orbit, by catching the bus. It's not a very efficient way of doing things. And here's why. If you want to procure a launch, buy the bus ride for your satellite, this is all the stuff you've got to do. I've had a go at this. It's really tedious and it takes a long time. I'm not going to expect you to read all that, and this is a huge simplification of the process. So my question over the last few years is, how do I catch that bus? Well, Oyster's not going to do it. Neither is space shuttles on the back of Irish £5 notes. You're going to need a lot of those. There's a lot of paperwork involved as well, usually more than the weight of the satellite you're launching. The problem really, and I go back to the picture of Newton's tree, in fact there's the plaque from earlier, there's the apple tree, is that it really takes a long time. Not as long as it takes to grow an apple tree, fortunately, but it can be the time it takes to go from a seed to a small sapling. It can be 2 or 3 years between you going, I want to catch a bus, and the bus turns up and how would you feel about waiting 2 or 3 years to catch the bus to go anywhere? You could forget buses overnight. That's what small satellites put up with. So in the UK, this is kind of what we need. I put it in dollars because most of the space community thinks in dollars. We need to be able to deliver a kilogram of stuff, a kilogram of small satellite into orbit for about $35,000, $40,000. We need a rocket that can do that, and it's got to be available pretty soon. Okay, we'll have possibly less access to European launchers. We'll have all manner of other trouble, no doubt, after next year. So we're going to need some rockets. There's a strategic importance and there's an economic importance. That's the two basic things we need: when and how much it's got to cost. That's a small satellite, by the way. That was the first one I worked on, LSAT-1. Then it's got to do some other things. It's got to be flexible, that launcher. It's got to be timely, less than a year, please, and that's still a long time to wait for a bus. Preferably, bits of our rocket shouldn't be subject to US export control, and friendly though we are with the Americans, they can in theory say you can't launch that rocket with that payload, you can't put a Chinese satellite on it, you're definitely not taking it over there and launching that. Sorry guys, it's not happening. So we kind of need critical items not to be subject to export control. And, crucial for the UK, it has to be safe. We are a very populated country. We're quite proud of what we have. We'd like to keep it intact, but we also want to do this satellite launch thing as well. So Sun synchronous orbit, which is a fancy version of the polar orbit that I showed you earlier, is our preferred orbit. That's ideal for a lot of small satellites. And we have to go from Scotland to do that. Although if we can use an aircraft, an airborne launch platform, so still something for the guys who like wings, then that may give us a bit more latitude. How are we going to do that? So this is the future bit, and the future is not yet written. You will hear some announcements within a month, I think, right after the local elections are finished. One bit of the future could be business as usual. So we catch the bus. This is quite an impressive bus. It's the PSLV launch vehicle from India. There is one Indian satellite in there. There is a bigger Indian satellite there, and there's all our stuff clustered around the bottom being gently levered into place. And that launched in January this year with Carbonite 2 and with a demonstration satellite for a Canadian customer, all built by SSTL. So the bus still works. The bus will still be there in the future, but let's face it, we're not going to grow our industry. We're not going to really succeed with just the bus. We could buy another country's launcher and bring it to our launch site. That's what Europe already does. So that's the Soyuz, built in Russia, the world's most reliable launcher with the most heritage. They cart them in a ship all the way over to Kourou from Russia. Heaven knows what they pay the Russians, and they launch them from there and put a European flag on it. Well, great. But again, you can see there are some supply challenges there, not least of which the relationship with Russia, the price you get charged, the fact that you don't really know how that rocket works, and if it goes wrong, the Russians could kind of go, well, too bad, you bought the wrong one out of the box, etc. We could rebuild this. I'm a firm advocate of this. We still have some of that knowledge. Whilst I wouldn't suggest going to museums and pulling all the stuff out of the archives, we know a lot of what we did, and we have a lot smarter manufacturing these days. We have 3D printing, we have CNC machining, we have some extraordinary tools at our disposal that could allow us to rebuild that cheaper, quicker, better, and we have the satellites to go in it, which we didn't have in 1971. And I think we'll need some of that too. But I think we've also got some other things, and this is now a very out-of-date picture, and I have spotted some reaction engines people in the audience, so I'm going to choose my words very carefully here. I'm also going to show a video which I was allowed to see while I was at Reaction Engines. It's nothing super secret. I'm not going to give away the secret of the heat exchanger or anything. This is a space plane. It's called a Skylon. It is revolutionary in more ways than I can even think. You think Elon Musk's got a cool rocket? It ain't nothing compared to that Skylon. We haven't built it yet. It's fully reusable. It embodies two power plants that are really the greatest advance since the jet engine. It's pilotless. It's the biggest drone in the world, or it will be. And it will deliver things to orbit probably for a factor of 10 cheaper than any other rocket we can imagine, including that Falcon 9. You know, that was invented over there. We didn't do that. This is a British invention. And right now, Reaction Engines are working on the power plants. They've got to get that right first in order to make all the rest of it possible. What could be possible if we could do that? So I've got a last video to show you. I don't know if this will work. Yes, it just might. This is a bit of future thinking studies. Let's go to Mars. This is what you could build if you had a Skylon and if you had the power plant to launch it. There's your space dock in orbit. You could put that together first. There are several Skylons, and you're putting together the tanks, the rocket engines, the crew modules, and other things. And apologies if I'm making people at Reaction Engines really cross, but I think this is just such an amazing video to tell us what we could do in this country if we get it right. We aren't going to do this in 2026. I think it'll take a little bit longer, but it's the possible. This is not science fiction. So if you want to go to Mars, perhaps in our lifetime, colonize it, find out whether there was life, make another home for humanity if we get it wrong here, all of this is potentially enabled by the future of rocket launch vehicles. I'll stop there because it does go on a while. Great piece of inspiration, and it's the sort of thing that's got me out of bed every day for the last 25 years, and I'm pretty sure it will do the same for the next 25 years. I'll leave you with one thing to think about. So we have some legislation that allows us to do launch from the UK. Back when I started my career, if I'd gone there and said, I have a rocket launcher, I want to launch from the UK, how do I do it? The answer would have been you can't. It's not just we don't do rockets, it's you cannot, there is no legal framework to allow launch from the UK. So we have produced this. This is not the most interesting document in the world to read. And again, I mentioned my wife is a lawyer. I did hand it to her and hope for a translation, and I think she didn't find it particularly exciting either. But we produced this. This was the draft. It has now been signed into law by the Queen. This is, if you will, the framework to allow us to do the detailed rules and regulations to actually allow launch from the UK. And, you know, sort of flippancy from Bernard von Braun aside, this is actually really important. The UK, as I've mentioned, is a busy place. A lot of people going about all sorts of business and having a good time. We have to get rocket launch right. Rockets are unreliable and they're difficult and they're dangerous, but with the right governing rules and the right forethought and perhaps the right technology, we can do all this. And it's going to be a pretty exciting next 10 years, I think. So, to leave off then, these are the things I've covered. I'd like to say thanks to Kingston University, who've put up with me and helped me pay my mortgage for the last 8 years and taught a few new young Turks a thing or two about rockets so that we're going to have a workforce in the future. My colleagues at Katina Space, who basically I picked because I like to work with them and they suffer in silence as I go on about rockets, and my rocket company, UK Launch Services Limited, and hopefully we'll be running the spaceport in the future, or at least one of them. 8:10, time for some questions maybe? Thanks for your attention as well.